everyone, my name is Dina and I'm part of the Immerse team at UCSB. In this walkthrough, we will be going over latent class analysis, the enumeration steps, and we'll go over some visuals and tables that you can create in R. To get access to these materials, all of our materials are on GitHub through this link. And you'll see on GitHub, we have our own Immerse project organization within GitHub, and then you can click on the repositories, and the LCA_enum or enumeration is what I'll be using throughout this walkthrough, specifically the .rmd or the markdown. And I'll be going through that step by step. To get access to these materials, you can either choose to fork the repository to your own GitHub or download the entire file directly to your desktop. Either way, we will be using all the files located in this repository. This walkthrough will be divided into 4 parts. The first part will prepare the data and look at some descriptive statistics before part 2, which is the latent class analysis enumeration, table of fit indices, the information criteria plot. Then in part 3, we'll compare class solutions and look at probability plots. And then finally in part 4, we'll look at classification diagnostics and observed response patterns. Okay. So once you have that downloaded, then you can look in the folder and then you'll see a lot going on. What I'll be using is the knitted HTML markdown, and I'll be walking through it. It's right here. And then as well as opening the R project, which has the markdown in it. And then I will be doing a live code along. Okay, so I have opened up the R project to get started. To open up the R project, I clicked on the R project icon here, and then now we have all the files located in R. There is another intro to R and RStudio video if that's helpful. To get started, what I'll be doing is opening up the markdown located in the folder, and this is everything that is shown in the HTML file. So I'm going to scroll through the code and then explain latent class enumeration as I go. This first part of the markdown just has some information on our Immerse project, how you can apply for next year, and ways to follow us on Twitter, and you can view our website. Okay. The example we'll be using in this video and other videos are bullying in schools. So this is a way to demonstrate mixture modeling with the training program and online resource components of the IES grant. We utilize the Civil Rights Data Collection, a CRDC data repository. So this data is currently available for selected latent class indicators across 4 years. And we are using the Arizona State sample. So the indicators that we are using are 3 variables on harassment/bullying in schools based on disability, race, or sex, and then 3 variables on full-time equivalent school staff, hires, counselors, psychologists, and law enforcement. So you can see when we scroll down that we have a table of the indicators we will be using for the latent class analysis. So these are the 3 variables on reporting harassment in schools, and then the last 3 are full-time equivalent school staff hires. So these are all binary variables. So you'll see a 0 for no reported incidents or 1 for at least 1 reported, and then for the last 3, 0 for no staff present, and then 1 for at least 1 staff present. And then we have some school identification codes. Okay. So here we have some information on how we coded the dichotomous variables. And then this is a latent class model with the indicators. So right before the variable description, we have a code chunk that loads the packages that we need to use in our analysis. So you would want to go ahead and run that before you run anything else, because if there is a function that is within one of those packages and it hasn't been loaded yet, then R will not be able to read it. Okay, so I'm going to scroll to the section of preparing data. This data set is within the repository, so it's under the data folder. And then inside that data folder, we see the .csv file. So what we're doing here is reading in the CSV, then we're using the pipe operator to add some more functions. The clean names function is from the janitor package, and it makes all the variable names within this data frame lowercase. And then this next function, so we're piping in another function, the select function, which allows us to select the 6 variables that we're interested in. And now we would have a new object in our environment, which is in the top right, and that will be labeled df or data frame underscore bully. When we run this, we'll see that we have the read in data frame with the clean names and the selected variables. Okay. Moving forward, some descriptive statistics. What's helpful? This descriptive statistics that are helpful to view with binary variables are proportions, and that's what we'll be doing in this set of code, in this next code chunk. So what this is doing is first reformatting the data that we just created called df bully. So what we'll do is take that object that we created here and create a new one called ds. And then we are piping in another function called pivot underscore longer. So this just rearranges the data frame to be long ways. I'll show what that looks like in a second. And then we are going to create a table of variables and counts, then find the proportions and round to 3 decimal places. Then we are going to make the table nice using a GT table, and then we can save it. So I'm going to run this whole thing. And then it's just telling me that it was successfully saved. And now we have a table of proportions for each variable. We can see how many people selected 0, 1, or there was no response, and the proportions. So as I mentioned before, this just reframed that previous data frame to make it long ways, and that allowed us to set up to make this table. Okay. Now we are in part 2. And first, before we get into enumeration, this would be a quick introduction to MplusAutomation, which is what we would be using to run our LCA models. MplusAutomation is an R package. It wraps around the Mplus program. So you need to have a valid Mplus license installed on your desktop or your laptop in order to use MplusAutomation. What it's doing is you're running the code in R, and it's communicating with Mplus to estimate your models. So it requires both R and Mplus software, and it does require some basics of both programming language. So you need to know Mplus syntax, and you need to know some R code. or R language. So a car metaphor for MplusAutomation would be that R Studio or R is the steering wheel or the dashboard, and M+ is the engine. Okay, so why should we use M+? It can provide clearly organized work procedures in which every research decision can be documented in a single place, and it increases reproducibility, organization, efficiency, and transparency. How the interface for MplusAutomation is entirely within RStudio. You do not ever need to open M+, though I would recommend you get familiar with it in case you do want to quickly bypass R and go directly into M+. You'll see why bouncing back and forth is not efficient. It's best to just do all your work in R, but sometimes you need to open it, so it does help to get familiar with M+, but this video will not do that. And the code presented is very repetitive by design, and you'll see that as we go along. So before is the template that we use for when running M+ models. They use the M+ object first, and then the M+ modeler. This is what creates the input syntax. So this is everything you need to write in order, everything you need to write to estimate your model. This last part, the M+ modeler part, estimates the model. So you don't need M+ until this last section. So it'll read this template and then model it or estimate it, and then create the input, output, and data frame that you need. Okay, so what we can do here is quickly fill in some of this template just to get an idea of how the formatting works before we get into the enumeration for our example. Okay, so what I'm going to do is start from scratch just to really walk through an M+, the formatting we use for MplusAutomation. So I'm going to take this away and really start over. You don't have to do this if you don't want to, but for the nature of the code along, I'm going to just type it all out. And then what I was going to say is usually we don't type the template from scratch. You'll take this, copy and paste it into your own work, and then work from there. But just for the sake of this walkthrough, I'm just going to type it all out. So the first object we are creating is going to contain the MplusObject function. So this comes from the MplusAutomation package, and we're going to name it mTemplate. You can call this whatever you want. And this mTemplate is going to be the input that we're going to use for the next function, which is MplusModeler. So the first thing we always start with is the MplusObject, and then we can insert some information in the MplusObject. The first M+ command that you always begin with is the title, and that would be whatever the title of your analysis is going to be. So this can contain whatever you like. Here we can do, we can call this M+ example for a 2-class model. So we are going to run a latent class model with this example right now, and then this next part will go into enumeration. But this is just to really understand how MplusAutomation works. Okay, so now within our MplusObject, we have our first command, which is the title. Then we put a comma right after our whatever is in parentheses. What you see in green here is always M+ syntax. Everything outside of the green, and this is only within the MplusObject I'm talking about. I'm not talking about the green you'll see later, but the information that's in quotes is always going to be M+ syntax. This will make a difference as we go on, but it's important to note that. Okay, the next command after title is the variable. So these are going to be the variables that you are interested in using for the model. You don't have to write out all the, if you're familiar with M+, you know that you need to have an option within the variable command that says names and lists all the names in order that they are in the data frame. You don't have to do that for MplusAutomation. So within the variable command, we also want to put quotes and a comma. So that's kind of the whole setup with MplusAutomation. You have your command, then an equal sign, and then the information in that command, which is an N+ syntax, then a comma, and then the next command. So the next command is variable. And what we want to do is usually two things. We want to first type in the use var option, which is the variables you want to use, and equals. And then now you want to write out what the variables you want to use for the latent class analysis is, or what they are. Unless you have them memorized, then you can start typing away. But say you don't have them memorized, but you have the data frame written. We know we're going to use the df bully because we prepared it up here, and this is the one we want to use. Instead of going maybe back and forth to make sure you're typing in the name correctly, we can go into our console, and this is what I usually do, and type in the names function, and then the name of your data frame. And then lists out all your variables that are in the data frame. You don't have to enter all the variables in your data frame in your use var statement, only the variables we want to use. It just so happens we want to use all these variables. So what we can do is, instead of writing each one, all 6, we can do a dash. So we can do report underscore dis dash LAW law underscore FTE. And then remember, this is M+ syntax. And after every single command or every single option within a command, you have to put a semicolon to let M+ know that you are done with that option and that you and to go next. The only time you don't have to do it is for the title. Okay. So now that we have the use var option, we also need to let M+ know that these variables are categorical. So this lets M+ know that when we eventually let it know this is going to be a latent class model, that it's going to be categorical and not continuous indicators. So you don't need this part if your items are continuous. So we would write categorical equals, and then all the variables that are categorical, and it's going to just repeat. Report underscore dis dash log underscore FTE, and then a semicolon to let M+ know that you're done. Again, the semicolon is only M+ syntax, not our syntax. Okay, and I didn't mention this before, but we have 2 options within the same command, which is variable. So we can keep going. You can organize this a little differently if you'd like. Maybe we can just stack them up on top of each other and then go to the next one. And this is letting M+ know what analysis you're going to do. And we are going to do a latent class analysis. So the way M+ knows that is through the classes option equals C, and then within parentheses the latent class model you'd like to run, and let's just do a 2-class model. So that's the format that you would do for an LCA model. Okay, so we are done with the variable command, and we are going to move on to analysis. And the equal sign, and then in quotes. So we can do the same thing here. And there are a few things that we can type in the analysis command. The first one, and usually the most important, is the type of estimator we're going to use. And for LCA, we want MLR, or maximum likelihood robust. There are other estimators that M+ uses that you can use as well. We can also let M+ know that we also want to let M+ know that the type of analysis that we're using is a mixture. We can adjust the number of starts or the starting values. And then we also included upping the number of processors. This just makes the analysis go faster. I believe the default is 1. This would be based on the laptop or the desktop that you have. Okay. So now we have 3 commands: title, variable, and analysis. The next one we can include is output. And this is letting M+ know what type of output you'd like included in the final results of your analysis. So we can ask for SAMP stat or sample statistics, the residuals. Tech 11 and Tech 14 has other fit information that we are interested in that we'll see later. So don't forget to put a semicolon. Then we'll add a comma. And then the final one, which we don't end up using because we use R to create plots, but M+ also creates plots, and MplusAutomation has some functions that can plot the information for you that came from the M+ estimation. However, what I usually do is plot it manually using R. So plot equals, and then we can do type equals plot 3, and the series equals report this dash law, and these are the variables we're interested in. This will create the item probability plot, but again, we usually do that directly in R instead of through M+. This is just one way to do it. Okay, so when we run this, nothing will happen. It'll just create a new object, a new M+ object called M_template. But the next part, which is this part, is what actually estimates the model. So if we run this, you'll see that we have a new object called M_template. And this has all the commands that M+ uses, and only populated the ones that we told MplusAutomation about. Okay, so then let's go ahead and create that last function. It is the MplusModeler, and we're going to create, or the object will be called M_template_fit. MplusModeler is the function, and then the first thing we want to let the MplusModeler function know is what information we need to estimate the model, which is that M+ object called mTemplate. The next thing is data out, and that's going to be the data frame that's saved directly onto your computer. So what we want to do is give it a location. M+ uses a specific type of data frame called a .dat file. So MplusAutomation creates that .dat file for you. You don't ever actually use it unless you actually go back into M+ and then run it directly in M+. But with MplusAutomation, it's going to use the data frame we created above. Okay. So to save that .dat file, we want to use the here function to let R know. So now everything right now is in R. R know where to save that file. And we can call, here allows us to work directly in our working directory. So it's going to start there, and then we'll let R know where to place it from there. So within our working directory, we want to put this new data frame in the M+ folder, which we have right here. It's already created. and then you put a comma and let R know what the name of that .dat file is going to be. We can just for now call it example.dat. And then we put a comma, and then the next thing is model out. And this is the same idea where we're going to save the input and output files, or the .inp and .out files. So within our working directory, we want to save those files in MPlus folder, and we'll call it the example. And then usually it's the .inp that we're labeling, and then that will also create the .out file as well. The next part are some arguments. The check equals true tells MplusAutomation to check if there are any missing semicolons. So sometimes we might forget to write in a semicolon. This will let you know if you did. That we want to run the model. Sometimes you can just create the input and output but not run it. And if we want to add a hash to the file name, when we create the .dat file, we usually type false. Okay. So now that we have this run, we can run the second one. And then we can just quickly read the error messages. So these two messages, this is giving me the information of the check equals true, and it's letting you know that the title does not have a semicolon, and we can ignore that because the title doesn't need a semicolon. What I forgot to do, and this is what it's letting me know, is that the data frame was not included. And that's exactly right, because I completely skipped the step right here. And so after plot, we would add another comma, and then we want to let R know what data frame we're using. And the use variables command is under, this is part of MplusAutomation, so not Mplus. So this is MplusAutomation syntax. So what we want to do first under the use variables argument is what the variable names are going to be. And the variable names are the column names of our DF bully data frame. And then the actual data that we want to use is called DF bully. Okay, so I forgot that. And I can run this whole thing. Great. So I have that first. So I have the same message. This is more of a warning letting me know that the title does not have a semicolon, and that's fine. But I do see an error here letting me know that I need to look at my output. And that's what I usually do. So I'll go into Mplus, and then I'll find that ex.out file, and then I'll open it, and then I'll scroll down. So this is all the syntax that we just created with that first object called MplusObject. And it's letting me know that this is unrecognized because there is no S in residuals for that. So now I can go back and rerun it. And hopefully we get a better solution. You can't see here, but right now we know that it's working because there is that stop sign. Okay, so now it looks like we're good. This is letting me know that there was a previous file called x.dat and it's being overwritten. So now what we want to do, that we have troubleshoot and we have completed our latent class model of 2 classes using MplusAutomation, we can go back to that x.out file and open it. You can also open this in Mplus if you wish, but good practice is to always open your output after every run, especially to make sure if there was any errors like there was before. So this is everything that we just created in our MPlusObject. It has that file extension, creating that .dat file I mentioned, the variable names. Our MPlusAutomation automatically recognizes the missing and it converts it to dots in the .dat file. These are the variables we've selected. We are running a 2-class model, and we can keep going. There are usually warnings in most output. For example, we can't have characters more than 8, variable names more than 8 characters, it cuts it off. So if the first 8 of 2 variable names are the same, then it'll get confused. That's what it's letting you know. Same for this plot, that's what's that's saying. And then finally, it's letting us know that that SAMStat or the sample statistics option is not available when outcomes are censored, ordered, categorical, or unordered categorical. Count, continuous time, survival variables. So it's letting us know that it's ignoring our request for SAMStat, but other times when you don't have only categorical, it'll still give you the sample statistics. Okay, so as we go on, I like to first check my number of observations or my sample size and the number of dependent variables. That usually kind of makes sure that that's like my first check to make sure that my sample size looks right and the number of indicators I've selected looks right. I usually just scroll down here. This is a covariance coverage, kind of letting me know about my missing data. These are the same proportions that we saw in our descriptive statistics. And then our log likelihood values, letting us know that the best value was replicated. Sometimes it'll say rerun with at least twice the random starts to check that the best likelihood is still obtained and replicated. So what you would do is rerun this with maybe double the start values and see if that message is still there. It doesn't know that you restarted it, that you reran it. So you might still be getting this every time as long as the best likelihood is still obtained, then you are fine. So then I go on to see some fit information. We're going to gather all this information in R, specifically the BIC and the sample size adjusted BIC or the ABIC. Then we go on in the output to look at the final class proportions for the estimated model. And that would be our class sizes. So we have about 78% for class 2, 21% for class 1. So this gives us our modal class assignment or the number of people approximately in class 2 and the number 1 and the number of people in class 1. Thresholds. And then our results in the probability scale is what we use to plot our item probability plots. So the probability of those in class 1 selecting category 2, or in this case, the number 1. So the number 0 is category 1 and number 1 is category 2. So the probability of those in class 1 selecting 1 is about 17%, 17.5% for this item. So report this being number of students harassed or bullied on the basis of disability. And then what we like to do is plot these values to get an idea of what that looks like for each group. and then some more fit information. And that's it. So every time you run an M+ model, specifically the latent class model, then you want to make sure you open the output. It should be like, as soon as it's done running, open it, make sure everything looks good, and then move on. Okay, so now that we have done a quick introduction to MplusAutomation, what we did was we only ran a single class model, the 2-class model. And now what we're going to do is enumerate 1 through 6 models for our example. So we already did the 2-class, but let's do 1 through 6. So as we scroll down to enumeration, we'll see that it looks kind of the same, but a little different. So we have that same exact format as we saw before. So from right here to here. So everything in what I've selected is not new, and then what is left is new. Okay, I just want to highlight that this is exactly the same besides what's in brackets, and I'll go over that in a second, but the next part is new. So instead of going back up here and then maybe changing this to the number 3, and then your input file, you would say C3, and doing that 6 times, what we can have R do is loop this entire MplusAutomation code 6 times and just replace the values necessary, like here and here, and maybe right here as well. Okay, and that's what the lapply function does. It loops through functions. And we're telling R that we want to loop through these functions 6 times. You can change this to whatever you'd like. You could change it to 5, 4, just the amount that, or if you only want to do 1. So say you want to do this one, the 2-class model that we did, you can just type in the number 2 here, and you run this and only loop 1 time, replacing all of the values with 2. So I'll quickly go over this in more detail. So before it was at 1 through 6. Okay. So we're going to loop through this code 6 times. And for each time, it's going to take the number and wherever is in K, wherever it says K, to replace that number, to replace K with that number. So what we'll see, it'll start with 1, and it's going to go through this code, and wherever you see in brackets K, it'll replace with that number. And to do that, the glue function is used. So it'll replace 1 here, 1 here, and 1 here. And then once that's done running, it'll go on to 2, 3, 4, 5, and 6. And then where it's going to live is in our enum folder here. So I've already run this, but we can run it together. You can't really see here because it's on my other monitor, but it's going through and running through 6 times. So you'll see here that it's working because this green line and it has the red stop sign here. So you don't want to do anything. You want to wait until it's done, until the red stop sign is gone. And you want to open every single output. You know that 6 models were run, so you want to have 6 outputs open. And I think I make a note of that right here. Before moving forward, make sure to open each output document to ensure models were estimated normally. And then, spoiler, the last 2 models did not produce reliable output and are excluded. So I'll open those to show you what that looks like. I think we are on the second to last one now. Okay, and now we're on the last one. And then we know it's done when this disappears and this disappears. Great. So we see those same warnings as before 6 times. We can get rid of these warnings, as it mentioned here, to add semicolons to all the lines, but you don't need a semicolon on the title. Okay, so I'm going to close all these warnings, and I'm going to make a habit of opening every output that for every model that was run. And like I said, I kind of do that check where I don't see any errors. So these are more warnings, same as what I mentioned before. I make sure that the sample size looks okay, and that I see this message that said model estimation terminated normally. Same, this is the same exact one that we ran before. 3. So this is just letting us know that the one or more logit thresholds approached extreme values. So this is okay. It still produced reliable output. And then now we have at 5. Oh, it looks like we are good with the 5 class model. Oh, and the 6 class model. Okay, so we can take out this last part. So there is no spoiler. Okay, so all 1 through 6 produced reliable output for this example. I think I was confused with another example. Okay, so then we can move forward. The next thing we're going to do is look at the table of fit. For each output that we are going to look at, they have their own, each latent class model has its own set of fit indices, and it's helpful for us to put them side by side in order to select a model for when we are evaluating all of them together. So we'll see here that each model has its own BIC, ABIC, and we kind of combine all of them into one table. So this first part of our code will extract each output that is in the file folder enum. So we can run that, Control Enter, and then an output bully is the object, which is right here. And then now we can see that 1, 2, 3, 4, 5, 6 models with the same file name are now in one MplusAutomation object. And if you open them, it has all the information that's inside our output. So this is helpful when you are plotting, creating tables, you're extracting that information directly from the output instead of risking an error when you are copying and pasting the values. That's the nice part about using R when dealing with Mplus. Okay, and this next part, we are going to extract the values. So right now we have them all located in this object. This next function, latex summary table, will extract the information. This last part was because I thought that there was only 4 reliable models, so I'm going to take that out. Okay, so now I have this next part, which I'm going to run using Control Enter or Command Enter, and clicking on the object to see what it gives me. So now this has extracted the title, parameters, log likelihood, BIC, ABIC, the BLRT, the VLMR, and the number of observations. So that is all located now in this nicely presented table, but we can go even further and then organize it even better. using R. Before we do that, this next part calculates the extra fit indices that we're interested in. So now here it calculates the CAIC, the AWE, and then it uses these, this is calculated in order to get the BF, the Bayes factor, and then the CMPK, or the correct model probability. This reorganizes the variables in the data frame and then arranges by parameters. So kind of in order to make sure it's still in order. When we run this, Control Enter and open it, now we have some more information in our table than we did before, because we calculated it using R. I'm just going to close all this. So now that we have all of our fit indices, calculated the new ones we're interested in, and put them all in a data frame, we can create a nice table that we can use for publication, and it automatically bolds based on the best fit index. So that's what the GT table does. I will make this a bit bigger so we can look at it. Okay. So when we create the table, we want to first create an object name. Here I'm calling it fit table 1. And then the arrow to create the object. And then I'm starting with that all fit data frame that we created that has all the fit indices. Next, we have the GT function. That's the table. That's the function we're going to use to create the tables. That is what creates all those nice tables. We have a header, and then we are relabeling the columns that are in the all fit. So wherever it says title here, we're just going to rename this in the table to classes, and that goes all the way down. We have added a footnote to be descriptive of what the fit indices are. And then the rest of the code gives conditional formatting for each fit index. So we'll see wherever is missing, we want to put a dash. We want to format the columns 3 through 7, which I believe are right here, to be to do 2 decimal places. Wherever the value is less than 0.001, which we'll see here, instead of listing it, we'll just replace it to less than 0.001. Same with anything larger than 100. And then all this is bolding the minimum value for each fit index. So wherever BIC is, for the column BIC between 1 and 4, so this is now going to be 6 because I thought we only had 4 classes, but we are evaluating all 6 models. For models 1 through 6, find the minimum BIC, and that's what it does for each fit index, the ABIC, CAIC, AWE, and the CMP. So that's what this part of the code does. If you have less or more than 6 classes you're evaluating, then you just want to change this number to reflect that. Finally, for the likelihood ratio tests, we are going to bold the value, the non-significant value in the table, and that's what this does. And I'll show you exactly what I mean in a second. And then we want to print the table. Okay, so now I'm going to run this whole thing. And we can see our nicely presented model fit summary table that went from this data frame to this with the bolded information criteria and likelihood ratio tests that were automatic because of the information we gave in our R code. Okay, so we know we want to look at the minimum values of the BIC, ABIC, the CAIC, and the AWE. We want to look at the model before the non-significant value for our likelihood ratio tests. Values greater than, I believe, 100, or I think it might be 10 for the base factor, and those closest to 1 for the correct model probability index. Okay. So we see most of the fit indices point to the 3-class model. We also see some evidence for the 4-class model. So when moving forward, the next thing we should do is look at the item probability plot for this class, and as well as the classification diagnostics and the response probability patterns. And we can do that next in this walkthrough. Okay. One thing we can also do is look at a plot of all of the information criteria. So that is what this code does. It takes that all fit data frame, selects 2 through 7, which is our parameters through the AWE, and then from there it wrangles the data frame, sets it up for plotting, and then when we run this, it plots it for us. So here's kind of like a scree plot where we want to see that elbow. We can kind of see it here at number 3. But this is just another visual for us when we're evaluating the model. And then in this part of the code, it'll take all of the class solutions and plot them side by side. So here's where we can look at the item probability plots for each latent class. Again, this is plots, though the probability of them endorsing the item. So if we look at one of the output and we scroll down, it plots these values, the category 2, which is that 1. Remember here, they're all 0s and 1s. So category 1 is 0, category 2 is 1, and the likelihood of them selecting 1 is what we're plotting or endorsing the item. So when we run this, we see the 6 plots for 6 models. I think it should readjust. That's okay. So we can see for the 1 class model, 2, 3, 4, 5, and 6, just to kind of compare, see if there's anything that stands out. We know that the 3 class model, we have more evidence for the 3 class model than the 4 class. So that's one way to evaluate your models. We can save this. Oh, I should probably go along here. Okay. Next. So the next thing we want to do is plot separately the item probability plot for our chosen latent class model. Here we've chosen 3. Sometimes it gets more less straightforward than what we saw, and in that case you would first, before plotting the selected model, is also find the observed response patterns and the classification look at the classification diagnostics, which is the last part of this walkthrough. and then try to build up an argument towards the solution that you find. For right now, we are going with the 3-class probability plot, and then the Immerse team, created a function to do that called plot_LCA text. You can adjust this or edit it to your liking if you want to maybe plot it in a different way. To do that, it's located in the folder, and when you open it, you'll see our code that creates a function called plot_LCA. And for this walkthrough, all you have to do is insert the model name, which comes from the output bully object, and then we want the class 3_bully.out, which we got from when we first extracted all of the models in that read models function. I don't think I went too into detail about this, but this read models function reads every single MplusAutomation or MPlus model, the .out file, and then compiles them and puts them in an object called output bully. So if we want to select one of those, then we would go directly to and say within output bully, I want this output. And so when we do that and we run this, we will get the output, the plot of the output that we selected. Okay, I thought it would be helpful to put the item probability plot side by side with the variable descriptions. Remember that what's being plotted here is the probability of endorsement of each item across class. So when we open up the C3 bully output under results and probability scale, we are plotting the category 2 value. So that is those schools that endorse the item across class. So one thing we can look at is perhaps this group right here, class 2. It looks like about 0.3. There's a 0.3 probability of endorsing this item, or the number of students harassed or bullied on the basis of disability. So if we go to class 2 and category 2, that's exactly right. 0.301 was plotted here. Okay. Another thing we can see is this graph plotted contains the class sizes. So for class 1, we have 24% in this class of the sample in this class, about 10% in this class, and 64. So when we are plotting the probability of endorsement across classes, it really gives us an idea of the heterogeneity of our latent variable. So in this case, we're looking at reports of incidents at the school level and whether or not faculty or staff were present. So that kind of gives us an idea of how to label our classes. So we see in class 2, there are high levels of endorsement for reported incidents, as well as at least one staff present. So a report of at least one staff present across these 3 variables. Here we have low endorsement of reports on harassment or bullying, but a high number of staff present. Here we see low endorsement across each of the indicators. So that is helpful to visualize our latent variable. Finally, the last couple things we want to do when evaluating the models is looking at the response pattern. So how are these students responding based on their class? And then some more classification diagnostics. This isn't a procedure for model selection, but does give you an idea of classification of the classes. And this code provides a table for that and some other statistics that you can look at when evaluating the model. Might be helpful when you're looking between two models, but this is, again, the fit indices are what are used for model selection. Okay. So within the observed response patterns, scroll down here. This is the table that we create. We need to rerun the model of interest and save the response patterns. So everything here should look the same as what we've done before, but we are going to create a new output that saves the response patterns. So this should look the same, but now we're selecting the 3-class model. We're not doing the loop because we don't need to. We are setting the starts to 0. The seed comes directly from the chosen, the best log likelihood value. So if we go to enumeration and then C3 bully, that value is right here. And that is what we'll use to replicate that same solution. The new thing we are adding here is the save data command. So what we haven't seen is the save data command that allows us to save the response probabilities. So the first option is the name of the data, the name that we are going to give the new data frame, which has the response patterns, and that is save data.dat. We want to save the probabilities, and that is what will give us the response patterns. And this will save the probabilities, posterior probabilities, and this will save the response patterns. Okay, and then we're using that same data set, and now we're labeling the output patterns.out. So when we run this, it's going to save in our M+ folder. And now we have a few things. We have that save data.dat, which gives us our data frame with the posterior probabilities. No, it's a .dat file, so they're kind of overlapping each other. So if we make this a little bigger, you can see that, but we do not need this. We need the response patterns probability. Right now it's not formatted nicely, so I can't really tell what it does. So let's read it into R. So this next part is similar to what we've seen before. We want to read in the observed response pattern data and label the column. Sorry, we have not seen this before. Like I said, when you look at the response patterns data frame, it doesn't give us the variable names, and it's not formatted in a way that we like. And that would be like this in a data frame. Right now it's in a .dat format, which really isn't helpful without variable names up at the top. So this is what this code does. It reads in the .dat file, this one here. And then it's just letting us know that there are no columns and that NA is at an asterisk. After that, we want to extract the column names directly from the patterns.out output. And then we want to paste them into that new data frame. Okay, so now we are going to run this. And what we've done was read in the patterns data, the table, extract the column names, and then combine them. And when we open up our data frame that we're going to use to evaluate the response patterns, we will see the frequency of each response. So these are all the responses by the students and their frequency. And then the posterior probabilities, as well as the modal class assignment. So what we're going to do next is create a table with the top 5 unconditional response pattern. So that would be the ones with the highest frequency, regardless of class. Then we're going to take the top conditional response pattern, top 5 of each for each modal class assignment. So this is going to order the patterns object by the highest, and then it's going to loop the patterns data to list the top 5 conditional responses for each class. It's going to convert the loop into a data frame and then combine the unconditional and conditional response patterns. So in our last object, we created a response pattern. So this is the top 5 unconditional, and then we have 3 conditional. So the first class, second class, and the third class. So we'll see 1, 2, and 3. Okay. Again, we want to use GT to make a nicely formatted table. This is similar to what we saw before, but now we are grouping the rows. We didn't group the rows in the fit index table. So now we want to group the rows for the first 5 being the unconditional response patterns, then the next 5 for each conditional response pattern. And that creates this nicely formatted table. This is just to give you an idea of how the students are responding based on their class. So without looking at class, the unconditional response patterns, we see a response of, or a pattern of 525 students not endorsing any of the items, which is pretty common to see people selecting 0s across or 1s across. And we see that the posterior probability is the highest for class 3, so the modal class assignment is 3. And then we'll see that most students are, the next highest response pattern is where students are not endorsing any of the items except that a psychologist was present. And that's how you would evaluate this all the way down. Here are the conditionals. So the top 5 for those who are in class 1, what are the responses looking like? And that's it for the response patterns. Okay, so now we're going to do the classification diagnostics for the 3-class solution. We are going to create a table like this that, here, I'll make it a little bit bigger, to organize all of those classification diagnostics. We're going to look at the class proportions, which we have seen before. Up at the top here. So we see that we have 10.6%, 24%, and 64%. This just gives us an idea of the class sizes. And then we have the confidence intervals for the modal class assignment proportion, the average posterior class probabilities, and the odds of correct classification, as well as entropy. So to calculate all of this, we need to rerun the solution again in order to get the bootstrapped confidence intervals. We add the bootstrap option under analysis and in the output. So here in the model statement, this is new, we are calculating the class proportions again in order for us to get the confidence intervals. So this is us calculating the K-class proportions and then getting the confidence interval for those proportions, and then adding it to our table. So when we run this, we get a new output called class.out. And then everything should look the same, except now we have those new parameters that we specified in our model. And these values should be the same as the K-class proportions. But when we scroll down to the confidence interval section, here. Now we can include that 95% confidence interval in our table. Okay, this next part is what organizes the table. We are extracting the information. Specifically, now we're extracting entropy, which we can get from the middle of the output right here. Then we can extract the confidence intervals. So this goes and specifically targets wherever it says new additional parameters, and then formats the confidence intervals with the brackets. And then we have the average latent class probabilities, which we take the diagonal of that table, which is right here, here, and here. And then we are extracting the modal class assignment proportion. Which we can get directly from the output as well, just right here. And then finally, we need to hand calculate the odds of correct classification using some of the information we have. Then we put everything together. So when we run this, we have all those values in our data frame. And then again, we use GT table or GT to make a nicely formatted table. So we have pretty much the same format, just making it into a nice table. And then we can also save it as well. Okay. And that is everything for latent class enumeration. If you have any questions, we can answer it via email or GitHub issue. I'm happy to answer any questions, and thank you.